Matna mo lihat. Tapos
আচ্ছা স্যার কি স্ক্রিন শেয়ার করছেন? মানে আমার হচ্ছে লাইক কোনো কিছু শো করছে না কলে। সো জাস্ট ওয়ান্টেড টু মেক শিওর যে আমার ডিভাইস ইস্যু করছে কিনা, তাহলে আমি ডিভাইস চেঞ্জ করতাম।
Hello. Am I clearly audible? Hello.
Yes, sir.
Okay, thank you.
Yes, sir.
Yes, sir, we can hear you.
Okay, then we can start our today's lesson. In our last lecture, we have discussed about recommendation systems and how to design the recommender engine. And over there, if you can remember that, uh, so for the recommendation systems, you need to find out the similar maybe items or maybe similar minded people. So similar minded people or similar items, if you want to find out that, then specifically if you have the larger data set, then it's problematic. Because for similarity measurement, at least you need to find out the pair. That means we can say two items, like maybe one is x1 and another one is maybe x2. The two items pair. So if we have a large data set, and on that case, loading the whole data set to the memory, actually it's cumbersome, okay? And sometimes the memory will not also support that. And as we already discussed in our maybe the few class before, that is if we can apply some form of swapping operation also, and that is also not useful because of the latency of swapping. So that's why we need some intuitive approach or intelligent approach so that we can find out the similar items even though our data set and data dimension is big. So that's why in this lecture we will discuss about one of the interesting approach that is called locality sensitive hashing. to find out the similar items, okay? To find out the similar items, even though the data set is huge. So not only in recommender systems, but also if you can remember our maybe second lecture, we have discussed about um, the market basket analysis. And for the market basket analysis, we have applied the a priori algorithm. And in case of the a priori algorithm also, we need to find out the similar items, okay? So that means we need to compare the items. So in that case also actually we need to find out the similarity and we need to measure the similarity also. Here is another example, like if you want to find out the similar image of this image, then in our we can see internet or maybe the image server, Google's image server, the billions of images are there. Then if billions of images are there in our Google server, then how can it will find out the similarity? So if you can think about the traditional approach, then maybe this is the image and then you have to convert it like maybe the RGB component, the R, you have to uh, find out those components of this image, R, G and B. Then maybe each and every images in that store or in that server, you need to also that is divide the components of those images R, G and B. And then maybe you need to convert each of the R, each of the G and each of the B kind of the one-dimensional form. And after that need to find out what are the closest or maybe similar possible images. So for that you need to find out the similarity or maybe the distance function you need to apply, and finally it will return few of those items, okay? Those are maybe very similar, or maybe it will check also a threshold of the similarity, and based on the threshold it will return you the similar images. So this is also another application of finding out the similar items or similar documents, specifically if we have the big data. So the problem is we have to find out the nearest neighbors kind of in high dimensional space, okay? High dimensional space. So several examples like pages with similar words. Try to find out the pages, web pages with similar words. Maybe customers who purchase the similar products, as we have discussed in our market basket analysis and a priori algorithms. And images with similar features, as I have already mentioned in this example. Okay, so that means the similarity measurement, or we can say finding the nearest neighbors, these are very common in today's world. So here is one example, that is the image example. Okay, maybe you can say one of the component of the image, this is maybe the R component. And for that, for each and every pixel values, maybe you can say this is the first pixel value, second pixel value, third pixel value, like this way, a part of the image. And then what we have to do, maybe we need to convert this one as just in one-dimensional form. Okay, so 1, 2, 1, and then maybe 0 to 1. So here the 0 to 1, and then 0, 1, 0. So 0, 1, 0. Okay. So now we have to find out maybe the distance between this image and maybe the image stored in the server. Okay, that component. And then using some threshold, like if the distance is less than this, less than the threshold S, then maybe we can say that those are the similar images. But the problem is this kind of naive solution, it will take longer time. Here is the n square, order of n square. So here n is the number of data points, okay, number of data points. I think we know why it is order of n square, because in our previous lecture we have already discussed about it. Uh, uh, that means we need the pairs, okay, we need the pairs. So if you have the data points like the n number of data points, then the possible pairs here, it is n times n minus 1 by 2. Okay, n minus n by 2. So these are the possible pairs. Um, I think we have already discussed it before. Like if we have just only 3 data points A, B, C, and we want to find out the pairs, then how many pairs are possible? You can see we can make the pair with A and B, and then we can make the pair A and C, and we can make the pair between B and C. So here we can see 3 data points we have. Then actually it is 3 times 3 minus 1 by 2. Okay, so it will be, so 3 times 2 divided by 2, and that is 3. So that's why if we have maybe n number of data points, then we will have the comparisons like n times n minus 1 by 2. So now we can see that if we write it using the notation, that is big O notation, and this is the case, that is n square minus 1. So n square n divided by 2, or n square by 2 minus n by 2. So here n square is there. That means in case of the asymptotic notation, we can write it like order of n square. Okay, so that's the naive solution. It will take the order of n square. This is huge because specifically for the big data, we can say the n, the value of n, if the n is maybe 1 billion or maybe the 10 million, then it will take huge time, okay, to just to compare. So now we need to find out some way. So we can maybe we can done the same thing with maybe this complexity order of n. Then we have to know how it is actually how we can do that. So one of the solution already I think we have discussed in PCY algorithm. If we can remember that. That is finding frequent item pairs. Okay, frequent item pairs. So for that, what we have done, I think no need to explain this one again, because we have already discussed it in the PCY algorithm, and we have also seen one example for that, the PCY. Okay, PCY example. We have 2 pass. In the 2 pass, usually we do 2 things. Okay, the first pass, counting items and hashing pairs. Okay, and then in second pass, then counting the candidate pairs. So these are the 2 things. So here the thing is we need the hash. Okay, we need to hash the pairs. If you can remember this example, that is transaction data set, we have like 4 transactions, and then we have applied a simple hash function, that is h of xy. It is x times y mod 4. Okay, so we have utilized this hash function here. So in this case, I think no need to discuss it again because we have discussed this one. If you can remember that the after hashing we will get the bucket, like here bucket 3, bucket here the bucket 3, then these are the bucket 0. So that means even though A and D, this is different pair, but we will get the A and D, and this is C and D, and also this is A and D, C and D. So those will be bucketed on the same bucket, that is 0. Okay. Okay. So that is this kind of hashing we need to apply also here in our uh, uh, that is the approach of locality sensitive hashing. Okay, locality sensitive hashing. So this is already we have done. So now the similarity measurement. For similarity measurement, in our last class we have also discussed about several similarity measurement, and one of the method we have discussed about the Jaccard similarity. So if you can remember that, there is similarity if we consider about one set is C1 and another set is C2, then Jaccard similarity, it will be that is count the union. Okay, so at first count the intersection divided by count the union. Okay, so like in this case we have uh, uh, this one, that one, and this one. So these three elements, those are actually common between set C1 and C2. So that is our the Jaccard similarity. If we can determine this one, the union, the intersection for using the intersection, we will get three elements, and then union, that means all the elements we have 3, 3, 6, 7, 8, total 8. So Jaccard similarity will be this one, 3 by 8. In case of the Jaccard similarity, it will define just only whether the word or maybe whether the item present in that set or not. Okay, so that's why the Jaccard similarity, maybe sometimes we can utilize it, but most of the time maybe we need to utilize some other similarity measurement methods also. In our last class we have discussed about it. So if we now consider about finding the similar documents. Okay, similar documents. If we think about finding the similar documents, let's say given a large number like n in the millions or maybe billions of documents. So for that, finding the similar documents, it will be very difficult, or we can say uh, specifically if we consider about our there is traditional approach other than the traditional or naive approach other than the big data approach. It's not possible actually to find out the similar items. So for that, what we can do, we can follow these steps. That is, at first we need to maybe prepare the shingles. So shingles means convert the documents into sets. Okay, and then we need to do the min hashing. So it will convert the large set to short signature, and while it will also preserve the similarity. Okay, it will preserve the similarity. So that means it will preserve the similarity. It means it will not provide the same similarity, but it will provide the similarity. Okay, that means not the same but the similar. By applying the min hashing, so this hashing function is crucial here in case of our locality sensitive hashing. Then utilizing this min hashed set, we will apply the locality sensitive hashing on it. So the locality sensitive hashing, it will focus on only pairs of the signatures likely to form the similar documents. Okay, so focus on pairs of signatures. So pairs of signatures, that means we will get signature from here, the min hashing, it will return the signature, and it will only focus on the pairs of the signatures. Okay, pairs of the signatures, and those signatures likely to be from the similar document. So usually we call those are our candidate pairs. Okay, candidate pairs. So that means instead of finding out the similarity among the whole documents or maybe large set of documents, so what it will do, it will try to find out the signature, and it will try to find out the similarity among the similar signatures only. Okay, so that means the similarity measurement on that case, it will be easier. Okay, now these three steps, the major steps, singling, min hashing, and locality sensitive hashing, how to do that, we will explain it. So that means we have the document. If we have the document, at first we need to do the shingling. After performing the shingling approach, it will return a set of strings of length k that appear in the document. Okay, so length k, so set of strings. So that means from the from the document, it will create the string, and each and every string will be maybe length like k. Then on that set of strings, we will apply the min hashing, and min hashing, it will return the signatures. The signatures specifically, these are the short integer. So short integer vectors that represent the sets and reflect the similarity also. Okay, so that means this set here, this set, the it will be replaced by the short signatures. Okay, short integer vectors, that is called the signatures. And shingling is another kind of features from the documents also. Like k shingles. K shingles means it's a k gram. If it will consider a document, and it will divide the document of a sequence of k tokens that appears in the documents. So tokens means it can be any characters, it can be words. Okay, sometimes you can consider also the sentences. Okay, uh, so think about, like, if we consider that a document D1, just a D1 consists of D1, maybe you can say D1. It consists of a word like A and B, then C, A and B. So this is just a word, okay, in that document. And then if we apply shingling there, the shingling there, then let's say we want just two shingles. Okay, the set of two shingles. We want the set of two shingles where the k, the value of k is 2. So two shingles means 2 gram. Okay, 2 gram, that means we have to think, we have to consider two characters at a time. So only two characters, like in this case what we will get, these two characters. Okay, AB. So here is the AB. Then we need to consider there is the B and C. So here is the BC. then we have to consider C and A. So here is the CA. Then AB. So as we can see, AB is already there, and we are creating the set. So we will not consider the same element twice in a set. Okay. So maybe you can say. So this is the shingle, and the shingle that is the K shingles. Okay, K is a two shingles. So two shingles here. Okay. So similarly, we can think about like we can create the K equal 3. So that means set of 3 shingles. We can consider this a set of 3 shingles also. Mr. Ataur Rahman, do you have any?
Yes, sir.
Yes, please.
স্যার একটু স্লাইডটাতে যাবেন স্যার।
হ্যাঁ।
স্যার এখানে এ বি বি সি সি এখানে দুইটা করে ক্যারেক্টার নেওয়া হয়েছে। আমরা কি রিপিটেড ক্যারেক্টার যেগুলি আছে, যেমন এখানে ডাবল এ আছে, এ এ দেন বিবি হতে পারতো, তারপরে আবার হচ্ছে এসি মানে সিএ আছে, আবার এসি হতে পারতো, এভাবে কি?
না, এটা হতে পারতো না। কারণ হচ্ছে আমাদের কনজিকিউটিভ টু ক্যারেক্টার্স কে নিতে হবে। হ্যাঁ,
তাহলে কি স্যার এই অ্যাপ্রোচটা এমন যে আমি এ বি কে নিয়ে নিছি, তাহলে আমার ফার্স্ট ক্যারেক্টার ছিল এ, তো এ কে আর কনসিডার করব না, এরপরে মানে স্লাইডিং উইন্ডোর মতো বি থেকে এরপরে।
স্পেসিফিকলি স্লাইডিং উইন্ডোর মতো।
জি স্যার, ঠিক আছে স্যার।
Okay, so we can create the shingles like this way. Yes. So this is we can call that is two shingles, a set of two shingles. So two shingles, that means the size of each and every set element is 2. Similarly, we can consider about the 3 shingles. On that case, it will be like S of let's say D2. If we consider 3 shingles, then 3 elements, the consecutive 3 elements we have to consider, like A, B, and C together. So A, B, and C together. And then we have to consider that is the next one, that is C, so B, C, and A. So B, C, and A. B, C, and A. Then C, A, and B. C, A, and B. So these are our 3 shingles. Okay, 3 shingles. That means each and every items of the set has 3 characters, and we have to consider the consecutive characters only. The name of the shingles usually sometimes we also call the gram, 2 gram, 3 gram, 4 gram. Okay, so those are our shingles. From any document we can prepare those shingles. Now from the shingles we can also each and every shingles can be represented using some hashed value. Okay, like AB, we can represent that AB is 1, and BC maybe is 5, and CA maybe 7. Okay, CA maybe 7. So that means if we can represent those shingles, then the equivalent the value or equivalent some numbers we can assign based on the hashing function. So it's better if we can hash the shingles. Okay, hash the shingles. But sometimes we can also just encode it like AB equal 1, BC equal 5, C equal 7, using some code, some kind of encoding. But if we apply the encoding, that's not the better approach, because we can say for each and every shingles you will need the numeric values for that. But if we apply the hashing, then maybe we can say AB and CA can have the same hash. Okay, same hash. I think we have the concept of hashing in case of the cryptographic hashing. Like if we think about a word like hello, okay, and for the word hello, if we apply some kind of hash function like the h1, okay, h1, some kind of hash function, then it will generate generate some numbers. Usually the numbers, those are actually bigger hash. Usually we call those are hashes. So maybe it will return like if 1 2 5 6 9 something. Okay, many more. Okay, so maybe you can say there is a 16-bit hash or 256 character hash, like okay. So hello, it will convert to a hashed value. Okay, so this is the hash. And if we check that the hello, if we spell like that, HELLOY, and then we present here a note of exclamation. Okay, note of exclamation. Actually, this is different from this. This is different from this. Then if we apply the hash function here, okay, then it will also create some hashed value, maybe F23540. Okay, so this hash function, this hash value. So generally those hash values are, we can say, the different. Okay, those hash values are different, and that's why in case of the cryptographic hashing, so that means whether someone changed the context of your email or text of your email or not. So usually we check that one, or we can say sometimes we can also apply the maybe MD, the message digestion. Okay, and for that we also check that is whether the digested text actually from the original sender or not. So utilizing those hash functions, a little bit change of the values will create the different hash. Okay, a little bit change, like this is hello and this is notation, that is the note of exclamation. So it will create two different hash values in case of the cryptographic hash. Uh, so that means now actually in case of our locality sensitive hashing, what we try to find out, that uh, this hello function, the hello word with note of exclamation, and this hello word without note of exclamation, we want that they will produce the similar hash value. Okay, similar hash value, not the different hash values in locality sensitive hashing. uh, so the goal is because these two words are very similar or same. Okay, very similar or same. uh, so if we can generate the same kind of the hash value, then we will find out the similarity between those. Okay, between those, by checking the hash values only without checking the words. Okay, but maybe you can say that that is, if we consider about the world, 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 hello world. Okay, so world. So this is the different word, and again for this case, the locality sensitive hashing will also produce different hash, because this is far from the hello, this word hello. Okay, so that's the target of our locality sensitive hashing. This is a little bit different from our cryptographic hashing. So I think we have already discussed about the similarity and Jagged similarity assumption. So what's the motivation behind here, locality sensitive hashing and the main hashing here? Suppose we need to find out the near duplicate documents. Okay, near duplicate documents, and consider that maybe uh, uh, in your data set you have like 1 million documents for that, and you need to find out maybe the similar documents. Okay, uh, so 1 million documents, it means actually the it is 10 to the power 6. Okay, uh, so 10 to the power 6 documents you have, so 1 million documents. Now if we try to find out the just maybe apply the naive approach, then how much time it will take to find out the comparison. So that's if we can uh, try to find out that value, that is how much time it will take to compare. So we know that for the 10 to the power 6, we need to compare like 10 to the power 6 times 10 to the power 6 minus 1 divided by 2. So these many pairs we will find here. So that means 10 to the power 6, 10 to the power 6 minus 1. That is n times n minus 1 by 2. Okay, so that's value. In that case, we can see 10, then here is 10 to the power 5, and then here is the 10 to the power 6 minus 1. Okay, 10 to the power 6 minus 1 divided by 2. So it will return like here the 10 and 2 is 5. So here 5 times 10 to the power 5 times 10 to the power 6 minus 1. So it is nearly, you can see it will be nearly like 5 times 10 to the power 11. Okay, so total we need that 10 to the 5 times 10 to the power 11 comparisons. Okay, so here is the 10 to the power 11 comparisons. So now think about like that is the here 10 to the power 5 seconds per day. So per day we have maybe just assume that or nearly 10 to the power 5 seconds per day, and 10 to the power 6 comparisons per second. If our computer can perform there is 10 to the power 6 comparisons per second. So 10 to the power 6 comparisons per second. Um, so that means you can see if we divide it by 10 to the power 6, then we will have like that means we can say 5 times 10 to the power 11. Okay, so we need this many comparisons, 5 times 10 to the power 11 comparison. Then we have to divide it by that is maybe per second. It can perform compare like 10 to the power 6. Okay, in such a case we will have like 5 times 10 to the power 5 seconds. Okay, so it will take 5 times 10 to the power 5 seconds. 5 seconds. So then how many seconds a day if we just divide it? Okay, how many seconds in a day? So if we just think about like the 10 to the power 5 seconds per day, I think we can find out that how many seconds in a day. So maybe you can say 24 hours, and then 60 seconds. Okay, 60 minutes, and then 60 seconds. Okay, so if we divide this one, okay, divide this one by this value, 24 times 60 times 60 maybe. Okay, and then nearly you will get the 5 days. Okay, nearly you will get the 5 days. So that means just only for comparison purpose, if you have just 1 million document, then it will take maybe the 5 days. Okay, just 5 days here. So think about if we have the 10 million document, then it will take more than a year for that case. So that's why in case of the large data, maybe we need something helpful, and without maybe comparing all the documents, it will compare only the selective documents. Okay, selective documents, and that's why we have to apply the min hash analysis. So we already discussed about the shingling. After shingling, maybe we will get a set of strings of length k, okay, length k, and then we want to apply the min hashing, okay, min hashing for that, and it will return the signatures, or maybe we can say the short integer vectors, and those signatures will also represent the set, okay, this set, and also it will preserve the similarity, okay. So preserve the similarity. Then how can we apply the min hashing? So for a min hashing, so let's say, how can we convert the shingles to a min hashing? So let's say we have maybe the documents. This is the document 1, and this is our document 2, and this is the document 3, and this is document 4. Okay, and we have the shingles. Maybe you can say specifically we will get many shingles, like if we consider about the that is the 2 shingle set. Okay, 2 shingle set. Maybe think about like SH, and then we will get maybe ED. So those are 2 shingles, and maybe TI, and maybe ES, then maybe the ST. Even consider some shingles like and the TION, the 4 shingles, and SION. So those are the shingles, okay? Those are the shingles. Now we can see in this case, this is document 1, and this is the SS shingle. Now we can see there is whether this shingle present in document 1 or not. So if present, then write here 1. So if absent, then write just 0. Like SS present in document 1, and maybe SS present also in document 2, SS also present in document 3, and SS also present in document, SS absent in document 4. Similarly, maybe ED present in document 1 and document 2, and ED, there is no ED in document 3, but that is in document 4, the ED is there. So in this way, we can prepare the our data set for the min hashing. Okay, so for min hashing specifically, at first we need to present our data set to find out the min hashed signature. So this is our data set. This is how we will present our that is the data and the in documents. Now what we can think about, like now we want to generate the min hashed, okay, min hashed signature. For that, consider that we have, this is the same data set, okay, this data set input matrix, that is shingles and documents. So these are our data set, and now we want to generate the min hashed signature. So the consider that total, maybe we have total shingles, like in this case we assume that just we have maybe 7 shingles. So this is the shingle number 1, okay, shingle number 1, and this is shingle number 2. Here is the shingle number 3, okay, then this is our shingle number 4, and shingle number 5, this is shingle number 6, and this is shingle number 7. Okay, so these 7 shingles in our document. Actually we have many shingles, but for this example consider that we have 7 shingles. Now for these shingles, okay, for these shingles, what we have to do, we can see we have total 1 to 7. The shingle numbers are 1 to 7. Now we have to do some generate some permutations of these 7 documents. Okay, so 1 2 3 4 5 6 7. Okay, So we want to generate some permutations. Or we can say we can apply also here the hash, that is hash, we can apply the hash function to generate the permutations also. So permutations, one permutation can be 1, 2, 3, 4, 5, 6, 7. So we can say there is maybe one permutation we can see it, we can consider it is 2, 3, and then 7, then 6, then 1, then 5, then 4. Okay, so this is the permutation, another permutation of these 7 instances. Okay, of these 7 instances, permutation of the 7 instances. Consider that this is the permutation. Actually, this is the permutation 1, the first permutation. Again, we have to generate the, maybe you can consider another permutation. Okay, another permutation here. Like again, we can apply some form of the hash function, and that hash function will generate also another kind of permutation. So again, maybe we will get the second permutation here. That means kind of the rearrangement of those numbers. Okay, so like we can get the 4, then 2, then 1, then 3, then 6, then 7, and 5. Okay, so those are our just permutation. Similarly, we can also think about the permutations, like another permutation of this. This is the 3, 4, 7, 2, 6, 1, and 5. So those are the permutations here. Okay, this is another permutation. So similarly, we can also generate many permutations. Okay, many permutations to generate the signature. So what it will do now, we want to generate the signature. Okay, signature from this matrix, that is our data set, and then utilizing our permutations. Okay, now here at first we can see, if we consider our first permutation, at first we need to find out the 1. So we can see this is 1 here, this is 1. So now we have to check the row. Okay, same row in our that input matrix or in our data set, same row. Then in this case we can see that is this shingle is present here in second column or in second document, and this shingle is present in also fourth document. Okay, so 1 and 4, 1 and 4. Now to derive the signature, what we will do, so 1, here is the 1, and this is our 4. So document number 1 and document number 4. So here is 1, we can write the 1 here, and document number 4 is also 1 there. Okay, these values are actually our number, this number. Okay, this number, that is we can say serial number or permutation numbers. Okay, permuted number. So 1. So here is we wrote the 1 here, and also here we wrote the 1. Now what we have to do, we have to find out the values in this row. Okay, in this we can say first signature. Okay, first signature. So all values. Okay, now we have to check the next. After 1 we have the 2 here. Okay, 2. So then again we have to check our corresponding shingle. So in this case we can see D1, it has, here is 1. So first column, first document, that means this shingle is present in first document, and this shingle is present also in third document. So present in first document and third document, that means first document and third document here. Then we can see we have to write this value. Okay, we have to write this value, that is the 2. So we have to write here 2, here is 2. Okay, here is 2. Now the second thing, that means we have to utilize the second permutation. So second permutation, and again we need to find out the, again 1, let's say this is 1, this is 1, and the corresponding values are here 0 1 0 1. Okay, so that means for this one we can say second document is 1 and third document is 1. These shingles, uh, uh, document 1 and document 2 has those the shingles. Document 2 and document 4 has that shingles. Document 2 and document 4. So for the second signature generation, document 2 and 4. So 2 and 4 we have. Now we have to think about the next serial, that is our 2. So for 2, we can see document 1 and document 4. Document 4. So that means document 1 here and document 4 is there. So now we have to write what? We have to write 2. We have to write 2 in document 1 and document 4. We have to write 2. So here we have written the 2 and we want to write 2 here. Okay, we want to write 2 here, but we will not write this one because we have to write the minimum value. Okay, so minimum value, that is the from the min hashing. Okay, min is minimum, so we have to write the minimum value. If we compare between 1 and 2, which one is minimum? Minimum is 1, so we should not write 2 there. Okay, so the 1 will be here only. Okay, 1. Then still you can see we don't have any signature item in case of our third document, and that's why we have to continue the searching. So now we have to search the next serial. Next serial is 3. Next serial is 3. So if the next serial is 3, then the corresponding shingles like ED, we have the ED here. Then ED, we can see the document 2 and document 4 has that values. Okay, document 2 and document 4. So document 2 and document 4, that is document 2 here and document 4 is here. Now we can write here 3. Okay, 3, but we can see there is we have to write the minimum one. So that means instead of 3, we have to keep the previous one. Okay, so still we can see the third document signature is missing, so we have to continue the searching. So later we will get what the next serial is 4. So the next serial is 4. Now we have to check the shingle. Here is 1010. Okay, so that means first document and third document. So first document here and third document is there. Okay, so first document and third document. In case of the first document, 2 is already there, as so that means 4, and here is the 2. 2 is the minimum, so we have to write the 2 there. And then for the third document, there is nothing written, so we have to add the 4, and we have to add the 4 there. Similarly, now we can see we got the signature. For that is the second signature. And then again the another permutation we have tried, like here in this case 3 4 7 2 6 1. Okay, now we need to find out the first serial number. Here is 1, and for 1 we can see it is the first document and third document. So first document is 1, and we have to put the one here in third document, in case of the third document also. Okay, third document also. Now the second serial, this is the second serial number 2, that is ED, and for that case here is document 2 and document 4. So document 2 and document 4, we can see there is no signature for document 2 and 4 already written for the third signature row. So for that case we can write here 2 okay, for that case we can write here 2 and 2. Okay, so and now we can see actually none of the there is no documents where the value of the signature is missing. So we got the signature matrix. Okay, so here is the signature matrix. So this is the signature matrix we will get. This is the signature matrix we will get from here. Now what we have to do from the signature matrix, we can check actually whether the signature matrix also preserve the similarity or not. Okay, similarity or not. So in our case, this is actually our document 1 and document 2, document 3 and document 4. So now we can see that if we compare between 1 and 2, so sorry, 1 and 3, the document 1 and 3, document 1 and 3. So if we compare document 1 and 3, that means this one and this one, these two documents. If we find out the similarity between these two, then you will get the 0.75. Okay, 0.75. Why you will get 0.75? Think about like Jacob similarity. On that case, document 1 and 3, we have how many commons? This one, and that one, and that one, and this one, and this one also. Okay, so 3. So like 3. And then the union. So here is this one, and that one, 2, 3, 4. So total 4. 0.75. The Jaccard similarity between this document 1 and 3 is 0.75. And then if we compare then that is the signature to signature similarity. Okay, signature to signature similarity. Maybe applying our our cosine similarity. Okay, so here is this one and that one. Okay, so on that case we can see if we compare the signature. Okay, think about this is document 1, document 2, and document 3 and document 4. Okay, document 1, 2, 3 and 4. And then again if we compare the similarity between 1 and 3, okay, document with the signature of document 1 and 3. So these are the values for that case, and this is another case. Okay, so these two. Find out the our cosine similarity. So if we apply the cosine similarity, you will get this one. Okay, 0.76. Okay, 76. Again, think about our similarity between 2 and 4. Okay, so here is the 2 and 4. Maybe think about our Jaccard similarity. On that case, we can see 0, 0, 0, 1. Okay, common is 1, 1. Here is 1, 1. Here is 1, 1. So you can say common 3. Okay, common is 3. And if we perform the union, so here union is, that means we will get another one, this one. So it will also return the same 3 by 4, that means 0.75. So here is the 0.75. Now if we compare our cosine similarity in case of the signature matrix, okay, so that means this 2, this 2. So we can see actually we will get the cosine similarity 1. Why? You can see this is actually the same vector. Same vector. Two vectors are the same. 1, 1, 2. Here is also 1, 1, and 2. So you will get the cosine similarity 1 for that case. Okay, for that case. So that's why we can see that if we apply the similarities like 1, 3, and 2, 4, those have some sort of the similarity. Then it will also give us the similarity of in signatures also. Like in documents, we have the similarity between two documents. And similarly, if we apply the similarity function to our signature matrix, so it will also provide us the same kind of similarity, not the same, but same kind or maybe similar kind of similarity. Actually, the length of the signature is also matter. Okay, so that's why sometimes maybe you will get some sort of deviation, some sort of difference. Some sort of difference is there. And we have also applied different similarity method, like this one is Jaccard similarity, and for this one we have applied the cosine similarity. Okay, so that's why the similarity measurement it will be a little bit different, but it will very close to the original similarity. And as we can see, there is actually we need to find out the similar items, and same similarity function we will apply uh, to all the signature matrices. And that's why those have the higher similarity and those have the lower similarity, that will also persist in case of our the similar signatures. Okay, so that's why it doesn't matter that whether maybe it is actually different from the original documents or not. But another thing is maybe it's kind of the trade-off, because you have the computational, that is complexity, and then there is huge computational complexity in case of the large documents. But when we create the signature, then signature will be the short, the length of the signature will be the short, and it's easy to compute. Okay, so that's why it's kind of the trade-off between complexity and then maybe the quality. Okay, so a little bit quality will be, you lose a little bit quality, but you will gain the faster processing ability to your models. Okay, so here after min hashing, we will get the signature. Now the next thing is, okay, we got the signature, then we can apply the locality sensitive hashing. Okay, locality sensitive hashing. Then what's it? Mr. Rejon Ahmed.
স্যার স্লাইডটা যদি একটু বের করতাম, আগের স্লাইডটা স্যার। জি স্যার, আমার কোশ্চেনটা ছিল যে স্যার এই পারমিটেশনের সংখ্যা যদি আমি আরো বাড়াই তাহলে কি আমার এই সিগনেচার ম্যাট্রিক্সের সাইজও বেড়ে
বেড়ে
যাবে?
যাবে, হ্যাঁ,
থ্যাংক ইউ স্যার,
সিগনেচার
ঠিক আছে।
ম্যাট্রিক্স সাইজ বেড়ে যাবে। ওকে, থ্যাংক ইউ। ইয়েস প্লিজ।
স্যার আমরা যে স্যার পিক করতেছি প্রত্যেকটা পারমিটেশন থেকে নাম্বারগুলো,
হুম,
স্যার এই পিকিংটা কি র্যান্ডম ভাবে করছি নাকি স্যার আমরা মানে সিকোয়েন্স ওয়াইজ লাইক 1 2 3 4 এভাবে আগাচ্ছি?
সিকোয়েন্সিয়ালি যাচ্ছি আর কি। আমরা প্রথমে যখন যখন আমরা নাম্বারগুলো জেনারেট করতেছি, এইটা হচ্ছে পারমুটেশন করে, যে কোনো পারমুটেশন নিচ্ছি অথবা হ্যাশ করে নিচ্ছি আর কি। কিন্তু আমরা যখন আমরা সিগনেচার জেনারেট করতেছি তখন সিকোয়েন্সিয়ালি যাচ্ছি। যেমন প্রথম সিরিয়ালটা আগে কনসিডার করতেছি, তারপরেরটা পরে কনসিডার করতেছি, তারপরেরটা তারপরে কনসিডার করতেছি, এভাবে সিগনেচারটা জেনারেট করার ট্রাই করতেছি।
স্যার এখানে নিউমেরিক্যালের জায়গায় যদি অ্যালফাবেটিক্যাল কোনো মানে অ্যালফাবেটস থাকতো তখন আমরা ওই অ্যালফাবেটের কি করে করতাম
না,
লাইক প্রথমে?
এই জন্য তো অলরেডি আমরা এটাকে কনভার্ট করে নিছি, ঠিক না? এই যে
আচ্ছা আচ্ছা
SH1 আছে কিনা, কারণ আগে তো এটাই ছিল, ঠিক না? SH ED এগুলো তো ক্যারেক্টারই ছিল, কিন্তু সেখান থেকে আমরা কাইন্ড অফ প্রেজেন্ট অর অ্যাবসেন্ট এভাবে ভাগ করে নিছি আর কি।
ওকে স্যার।
কাইন্ড অফ এটা হচ্ছে আপনার এনকোডিং অর কোয়ান্টাইজেশন করে নিতে হচ্ছে আর কি। ওকে, দেন নেক্সট we have to discuss about the locality sensitive hashing. Okay, locality sensitive hashing. Then what's the locality sensitive hashing? So what's the general idea? I have already mentioned. Use a function that is f of x that tells whether x and y is a candidate pair or not. Okay, so that means we have to use some sort of the hash function here again, and then that hash function will return maybe a block. Okay, the hash block. And if we can find out that that is maybe two signature, or the part of the two signature will be in the same hash bucket, then we will only consider those are actually our maybe the similar signature. Okay, and we can find out the similarity of those signatures only. So for that, what we have to do, where is this? Yes, okay. So for that, what we have to do, we have to partition the M, that means we can say M is our signature matrix, into the bands. Okay, bands. Again, why we are partitioning? Because we can say that maybe even though it's a signature, then it will not actually it will not we cannot load even the signature matrix to our memory. Okay, so that's why it's better if we can do some partitioning on our signatures. So that's why the matrix M, it will divide or partition into a B bands. Okay, B bands of maybe R rows. So you can define the value of the R and define the value of the B. Okay, define the value of the R and define the value of the B. And here that is the column pairs are those that hash into the same bucket. It will be that is greater than or equal one band. So now I think it's better if we can see it here. So let's say this is our this is our M. Okay, this is our M. So we have this M, and now we can see 2141. Okay, so here is a 21 sorry, 2121 and then 2141, 12 and 21. So these are our signature matrix. So let's say we have where is this here? So here is 2141, then 1212, then 2121. Okay, so this is our signature A, and this is our signature B, and this is our signature C. Now what we have to do, we have, maybe we can say we divide our M. So this is the M, divide our M into B bands. So let's say B equal 2. So that means we will divide the M into 2 bands. So here now, so in this case B may be 2, and then we can see this one, the 2 and 1, this is in band 1, and 4 and 1, this is actually in band 2. Okay, so 2 1 and 4 1. So that means we have divided our signature. This is the signature A. This is the signature A. We have divided into 2 bands. So each and every band we will get the list, the number of rows here also 2. Okay, R2. So that's 2 rows in each band. So it means maybe we have the memory here. This is our signature matrix, and then we will divide each and every signature into B bands. B here considering the 2, then 2 1 and 4 1. Okay, so what we will get here is our band number 1, and this is our uh, band number 2. Okay, so just 2 bands we have. Then in first band we will get 2 and 1, and the second band we will get the 4 and 1. Okay, for the signature A, similarly for the signature B, signature B, another signature, we will get also, it will divide like 1 2. Okay, sorry, 1 2, and then again 1 2. And for our signature C, again we will get 2 1 and 2 1. Maybe here is a 2 1 and again 2 1. Okay, so in this way we will get, that is the matrix M into B bands. So we have divided this each and every signature into B partition. Okay, so that means we have divided the M into B bands. Then we will get the signatures like this way. Okay, so like this way we will get the signatures like this way. So next what we have to do, so we can see there is, maybe this is the signature A, this is the signature C, like this way. Okay, each and every band we will get something. Okay, now the next thing is we have to apply again the hashing. Okay, again the hashing. So here is, this one is maybe you can say our signature, the signature A, and this is our signature B. This is our signature B. So the signature A, we have 3 rows here. We can say 3 rows, but in our case, actually we have signature A considering just we have 2 rows. Okay, the 2 rows, that is 2 1. So 2 rows. So in our case, it is 2 1 just only. For signature A, we have 2 1. So 2 1. And then we have to apply some form of hash function here. Okay, some form of hash function. And then this hash function that is based on the 2 1, it will return a value. Okay, it will return a value. Maybe you can say that value, yeah, whatever the value is, it will we will get here. And then again that is our this is for A, and considering our another signature, that is B. For B, we will get this, that is 1 2, and again the 1 2. So 1 2 and 1 2. Okay, so here is also 1 2. So 1 2 and 1 2. So that is the 1 2. And then 1 2. We have to apply the hash function. Then it will return also some value. Let's say this is the value for that, okay, and this is the value for the previous one, okay. That means those values are different, okay, those values are different. Okay, so now you can see that there is the for this part we will get this the bucket value, and this one we will get another bucket value for the hash function, okay, for the hash function. Now we can see that is we have also another part of our signature, okay. So this part, the band, this is 4.1, maybe you can say the 4.1 is here, and then hash it, and then it will get we will get something, okay, some values here. And then again we have to think about our there is our next part of the B, maybe it is also 1 2, and then hash it, okay. After hashing we will get some values here, okay, some values there, okay. Now similarly, maybe this is between A and this is between A, there is signature A and B, these two. Similarly, we have to think about like then A and C, okay, A and C, and then B and C, like this way, okay. And then we have to find out whether we will get those hashed value on the same bucket or not, okay. Like here in this case those are different buckets, okay, those are different buckets, but in this case we can see that is we got the values on the same bucket, okay, values on the same bucket, values on the same bucket. So if we got the values on the same bucket, then we have to measure the similarity between those two uh, signatures, okay, those two signatures. So that means we can see as though those are in the same bucket, so we will only consider those are our candidate pairs, because uh, uh, a part of the signature actually they have the similarity, okay. So maybe we those documents also, or we can say the equivalent signature also, they have the similarity, okay. So then we will determine the similarity between those um, signatures, okay, signature A and B. So if we can see that the nothing is comparable, or you can say for the hash function, generating the hash function, those are actually generated different things, then we will not consider those to compare the similarity among those documents, or maybe the signatures also. So again, there are several hash functions. I think we have already discussed about the hash function also in our PCY example, the PCY, I think, the PCY example, like this is the hash function, okay? So if we have like the uh, like 1 2, so apply this hash function there, okay? This hash function there, then it will be 2 times, sorry, 1 times 2 mod mod 4, so that is it will return the 3, okay, it will return the 3. So that means this is the bucket number, this is the bucket number 3, okay, bucket number 3. So similarly, maybe we can also think about here, this is 1 2, then 2 1, and then 4 1, okay, consider the 4 1, consider the 4 1. So 4 times 1 mod of 4, so it will return 0, okay. So this is the bucket number 0. So that means if we get the same bucket, okay, same bucket, if we get the same bucket for the 4-1 and for this one also. And then that means we have to measure the similarity between these two, signature. Okay, measure the signature between these two signature. And we will not maybe measure the similarity on the other signatures or other documents with other documents. So it will reduce the number of documents significantly. Okay, as we have already applied the min hashing to generate the signatures, and as we have already proved that the signatures also kind of the representation of the original document similarity, because it will preserve that. So there will be no issue if we can just maybe measure the similarity within the signatures also. Okay, within the signatures. So it will maybe return the close to the optimal similar values. So this is how the locality sensitive hashing helps to measure the similarity between or maybe among different items and item sets also. So as we can see that actually for the documents, for measurement of the document similarity, we have to perform the shingling. Okay. So actually, for the case of our data set, that is for the case of our recommendation systems, so recommendation systems, sometimes we need to measure the similarity among the items. Okay, and item similarity, or sometimes we measure, or we need to find out the similar minded people. Okay, for similar minded people or maybe similar items also, actually no need to find out the shingling values for that. So that means instead of finding out the shingling, already we will get the features. Okay, we will get the features, and from that feature we can just generate the min hashing, and then after that we can apply the locality sensitive hashing for that. So that means if we have the documents or maybe the texts, then from the documents or from the text, maybe we need to find out the features. But as we can see that we have already the ratings of different users, and then we can apply the min hashing there. Then it will create some signature, and then apply the locality sensitive hashing, and then find out the candidate pairs. Then only we will find out the similarity among the candidate pairs only. Okay, so we will find out similarity among the candidates only. So we will not measure the similarity with other users, only the candidate pairs for that case. Okay, so that's, I think, our locality sensitive hashing. So if you have any question.
Sir, প্রশ্ন করা যাবে? I had my hand raised.
Yeah, please.
Sir, so মানে shingling, we will only use shingling when we're looking for like similarity, but if we have like similar minded, in that case we don't have to use shingling.
Yeah,
right?
yeah. Yeah, because already they've.
In that case, we would just use my ratings given by the similar minded.
Yeah, actually, you need to use the ratings only. Okay, any other question? Okay, I think there is no question from your side because this is one of the easy topics. So just the min hashing, and then maybe we need to find out the candidate pairs through locality sensitive hashing. Okay, so this is how we can generate maybe our the similarity among different users or maybe different items also. So that's all in our today's lecture. I think if you don't have any questions, then we can stop our lecture here. Thanks everyone for joining.
Thank you for your time.
স্যার রেকর্ডিং কি আমাদের কি এটা রেকর্ড করা হয়েছে স্যার?
Yes, we have the record and I will upload it.
থ্যাংক ইউ স্যার।
Thank you very much.
Sir, what about attendance of today's?
স্যার রেকর্ডিংসটা কোথায় আপলোড করবেন?
In Google Drive, I guess, right?
Yes, I will upload it in our Google Drive. That is the course repository. So attendance for all, okay?
Oh, all right. Thank you, sir.
Okay. Thanks everyone for joining. See you in our next class. Bye.
Thank you, sir.
Assalamualaikum sir.
Thank you, sir.
আসসালামু আলাইকুম স্যার।
Sir.
Alaikum salam.